This is the second application that we're going to talk about for change of bases, and this is what we call the Wronskian. I think it's one of the greatest names of any mathematical item, the Wronskian. The Wronskian shows you whether functions are linearly independent. So I wrote a couple of notes up here so you don't have to just sit here watching me write things on a whiteboard. Suppose I've got a set of functions, and each of those functions has at least n minus 1 derivatives. You could have more, but you can't have fewer because you'll end up with rows of zeros. So we're going to define the Wronskian as a determinant. The Wronskian will be a determinant where we start by putting our functions up across the top row. So y1, y2, y3, all the way till we get to yn. Then from there, we're going to take a derivative. So we're going to take the first derivative of y sub 1. We're going to take the first derivative of y sub 2. We're going to take the first derivative of y sub 3 until we get to the first derivative of y sub n. Then we're going to take the second derivative and so forth until we get to the n minus first derivative of 1, the n minus first derivative of y2, and the n minus first derivative of y sub n, which is why we need to have at least n minus 1 derivatives. Then you evaluate the determinant. So that is the Wronskian. Once you have that written out, then evaluate. And you notice I put it with those two bars on the side. Those two bars on the side say it's not a matrix, it's a determinant. So you should use those rules for determinants to figure out what the determinant is. Now, the determinant could be a number. The determinant could be another function. Here's the question. Is the Wronskian 0 for all values of x? So if the Wronskian is 0 for all values of x, we have a name for it. We say it is identically equal to 0. Why that language? Because what if the Wronskian comes out to be like 4x squared? Then what do you do? If x is 0, then yeah, the Wronskian is 0. But if x is anything other than 0, then no, the Wronskian is not 0. So we need it to be identically equal to 0. So we need it to be 0 for all values of x, which basically means we need it to be 0. So if the Wronskian is 0 for all values of x, then it's identically equal to 0. So what does this do for us? Well, here's the rule. If the Wronskian is not identically equal to 0, then all those functions you started with are linearly independent. So if the Wronskian is not identically equal to 0, then the y sub n's are linearly independent. Oftentimes you'll use this in differential equations when you're trying to figure out whether the results of your solution are linearly independent. So can you write it as c1y1 plus c2y2, or are they actually linearly dependent solutions, and the Wronskian is used to test that. All right, so let's take a look at a simple example. Suppose I give you two functions. Function 1 is x, function 2 is sine x. I'll bet you can look at that and realize that they're not linear combinations of each other, but let's try setting up the Wronskian to show how this works. Across the first row goes our original functions. Across the second row goes the derivative. So the first derivative of x is 1. The first derivative of sine is cosine. Now evaluate that. So find the determinant. X times the cosine of x minus 1 times the sine of x. This is not identically equal to 0. So it's not 0 for all values of x, right? That upside down A means for all. So it's not 0 for all values of x. Therefore, those two functions are linearly independent. All right, let's take a look at another example to see how this works. Suppose I gave you these three functions. The first function is 1. The second function is x squared. The third function is 2x squared. Well, right away you can see where this is going. If I take function 2 and multiply it by 2, I get function 3. But let's see how this works in terms of the Wronskian. So across the top row, I got 1, x squared, and 2x squared. Across the second row are the derivatives. So the derivative of 1 is 0. The derivative of x squared is 2x. the derivative of 2x squared is 4x. And across the third row, I got 0, 2, and 4. In this case, it would be easier for me to iterate down the first column than across the first row. So I'll end up with 1 times 2x, 4x, 2, and 4, and then minus 0 plus 0, because these two values here, if used as coefficients, are just going to give me 0. So this is going to give me 1 times 4 times 2x is 8x. 4x times 2 subtracted is also 8x. That gives me 0. It gives me 0 for all values of x. No matter what I put in there for x, I'm getting out 0. So this is identically equal to 0. These are linearly dependent. Because for every value of x, I get 0. All right, let's try this out with the differential equations example. Now, I'm doing this in such a way that some of you have taken diffEq, some of you have not. So I'm going to set this up in such a way that you don't need to have taken differential equations to understand this. A differential equation involves a function and its derivatives. So I may have a differential equation that looks like this: y double prime minus 2y prime plus y equals 0. So my claim is that if I ran through a whole series of solution methods, the solutions are e to the x and x e to the x. The first thing I can do is I can confirm this. What is y prime? So if I do it for e to the x, y prime is e to the x, y double prime is e to the x. So if I go back into my original equation, I'll get y double prime minus 2y prime plus y, right? These solutions are your y's. And it works. Try it for x e to the x. This gets more complicated because if I start putting in second derivatives, then I'm going to need product rules when I put in those second derivatives. But it turns out it works for that also, right? You'll do it, you'll get a 0 on the other side. All right, now let's see if those solutions are dependent or independent. So are the solutions that I came up with linearly independent? Set up my Wronskian. So my two solutions were e to the x and x e to the x. Take my first derivative. My first derivative of e to the x is e to the x. The derivative of this, here, let me do it over on the side here so I can write it in there a little bit neater. Let's write this: if y is equal to x e to the x, then y prime is going to be keep the first, derive the second, derive the first, keep the second. So I can write this as e to the x times x plus 1. All right, let's evaluate my Wronskian. When I do that, I'm going to get e to the x times e to the x times x plus 1 minus e to the x times x e to the x. Let's simplify this a little bit before we start making a bigger mess out of this, because it's really not that bad. E to the x times e to the x is e to the 2x. So I get e to the 2x times x plus 1. Over here, if I rearrange terms, take these two x's to the front, I get e to the 2x times x. Now pull out an e to the 2x out of the entire line, and I'm left with x plus 1. When I pull an e to the 2x out here, I'm just left with an x. And now the entire thing in parentheses go away, because x minus x is 0, and 1 times e to the 2x is e to the 2x. Notice that this is not 0 for all x. It's actually not 0 for any x. Which means what? Which means that the solutions are linearly independent. which means what else? I can write the general solution, and if you're taking differential equations, maybe you've seen this and now you're starting to have flashbacks. I can write the general solution as y equals c sub 1 e to the x plus c sub 2 x e to the x. So that's what the Wronskian is. It tells me that those two solutions are linearly independent or linearly dependent, and then that allows me to write my answer in certain ways. That's the end of this. Actually, this is the end of chapter 4.